So we're going to set up a point charge simulation using Maxwell and use this demonstration to verify Maxwell's first law. In a previous segment, we did an analytical representation of that and worked through the vector algebra, I guess, and the calculus to quantify the charge enclosed by a sphere of a point charge. We're going to do the equivalent version of that inside a tool called Maxwell. So in Electronics Desktop, I'm running version 22R1, and we just have an empty space here where we have to insert a design type. So all I've done so far is just open the software. You should see a very similar view. If not, you'll probably have to just insert a new, and you'll get this project indicator. So the first thing we want to do is go over to Maxwell, and if we drop down, there's a few options. We want the very first one that says Maxwell 3D, and when we do that, you'll see over here in our project tree, we now have this top node that defines the name of that design type, and now might be a good name to save this project and give it a meaningful name. I'll probably do that as we go along. So I'll try to point out a few things of the features of the software as we go, but it really wasn't designed to be an extensive introduction. If we need that at any given point, hopefully I'll refer to some of that at the end of this demonstration about where you can get more help on that. So one thing that I'd like to do is just give a quick, if you look at my windows, the way that they're set up, I've got a project manager window, a properties window, my message manager, and my progress window are all laid out in this fashion. And if I go to view, I can see all those windows are toggled on. So if yours doesn't look that way, you might go ahead and make it similar, and you can get the same sort of configuration that I have, and you can certainly see resizing some of these windows as you see fit. And you'll notice that things will pop up in the manager and the progress bar as we go through, and we'll also build out these trees as we go. So we happen to be in the draw tab right now. As you click around the different tabs, you'll notice that the buttons will change, and that'll be important to us as we move through the setup of this simulation. So what I'd like to start with is set the solution type. So when I go up to the menu that says Maxwell 3D, up at the very top, the very first thing I want to do is choose a solution type of electrostatic. And that's the one that we want if we want to evaluate fields that are emanating from a body that has a charge associated with it. And that's exactly what we're going to be doing. So once we OK that, everything else should be good. You should see here that we have the grid turned on. So you're looking at a grid in the XY plane. We could turn that grid off. You can mess around with these different settings here, but you'll notice that if I expand out, we'll be using some of this as we go on, but we have our single coordinate system. We talked about the Cartesian coordinate system earlier. We've got an X, Y, Z indicator here, and we'll also notice that there's planes, and these are basically imaginary planes that are following these the normals of those coordinates. We'll use those to project fields onto in a bit. So the first thing we want to do is set up the geometries. There's going to be a few different geometries that we need. The most fundamental thing that we need is what represents the point charge. There's actually no way to assign a point charge in Maxwell, but what we'll do is we'll make an equivalent small sphere that will be representative of a point charge. So I'm in the Draw tab right now, and if I go to this icon that says Draw Sphere, when you hover over it, then all we have to do is click that, and now you'll see in the interface it's looking for a place to drop that location. I'm going to put it right at the global origin, so it should click right to that spot, even if your grid is not on. And when I do that, I'll hit the left mouse click button, and now it wants me to drop a location for the sphere. And this is going to be the radius ultimately. And what I want to do is I want to make the radius 0.5 millimeters. So it turns out I can drop this anywhere, and this is a good trick. I'm not going to worry about the number as I put the sphere down, because I'm going to come and make an adjustment. So you'll notice here that in my modeler tree, my sphere got assigned to this property of vacuum. And as I click on this lower node that says create sphere, then I can change the location and I can change the radius. I happen to select a radius of 1 without studying it too hard, so I can just as easily in the properties panel put 0.5 in, and now I know I have what I was looking for. As I select as I hit enter and I select that object, whenever I select something, it highlights for me. I can always hit Control, select for it to unhighlight. If you're on a virtual machine, the keys could be different. Sometimes we've seen the command symbol would work, or sometimes like an like an ALT key would work. So you might want to just get oriented with that. And now that we're here, I'm going to go ahead and assign the charge to it. So I selected it by left clicking. Now with it selected, and by the way, just a real quick reminder, if I come outside and click in the dead area, you'll often notice down here in the bottom, this will give us good feedback about maybe what phase of an operation we're in. So if I click, it will give me feedback that tells me at least one object is selected. So sometimes that comes in pretty handy. So with it selected, I will right click, and now I'm going to go to this assign excitations. And if you change the solution setup, like one of our very first steps, you should see charge is available. So I'm going to choose charge, and I'm going to make it 1 coulomb. So I type in 1, I'll go ahead and leave the name. And after doing that, you'll notice that over here in my project tree, this can be opened up now. So under the field of excitations, I have 1 excitation, and it's giving me the feedback as to what I just put in there. So whenever I highlight that node, it should graphically highlight it as well. And as you'll see, we're about to add up another excitation in here. So the way the simulation works in finite elements is that we actually have to assign what the background condition is. So I said earlier that we were going to do a charge in free space. We have to define what the boundaries of that free space is. So to do that, I'm going to calculate this. I'm not going to calculate. I'm going to insert this region. So up here, again, we're still in the Draw tab. You'll see right up here, kind of in the middle of the ribbon there, we have this button that says Create Region. So I'm just going to hit that button, and I'm going to choose basically a bounding box that is going to be set up around this point charge. So I'm going to choose absolute offset instead of percentage offset, and I'm going to make this 50 millimeters. And I'm going to say pad in all directions, and you'll see what that means as soon as we hit OK. And you'll notice that it's kind of hard to see the screen now because the thing that we just created automatically got selected. If you come up here back in the draw, back in the ribbon, there's a number of things that are very helpful. We can hide things and show things from view. Sometimes showing all makes sense. And you'll see me come back and forth between these functions just to be able to see objects as some of them get buried inside of other objects. What I'm going to do right now is say fit all, and now I'll click outside the dead spot, and what you see is a really large bounding box. And you'll also notice that it got assigned to this material of vacuum as well. So we have a sphere in the center, a very small sphere that's just a 0.5 millimeter in radius, and even though its property is air, it still has a charge distributed. So everywhere throughout this sphere, basically that 1 coulomb has been distributed. So 1 total coulomb of charge is assigned to that sphere. And in our air region, in this case, we don't have anything assigned yet. But that's where the next excitation is going to come in. So when we apply a voltage of 0 to the perimeter of this box, then it's basically treating it as if this point charge is in free space. So let's do that, and I'm going to, it's important that we select the faces of this object. So when I choose the object itself, it'll tell me that there's an object selected, but instead of selecting the object, if I left click or deselect, I can choose my selection mode. So all I did was I right clicked in the dead spot and I went to selection mode. And instead of choosing objects, I'm going to choose face. Now with faces selected, I'm going to hold the control key down and I'm going to choose them. While I hold the control key down, it's going to keep appending these faces. So you can see right now I've got 3 faces selected and I want to have all 6 selected. So as I go around the object, I should be able to see that once I get all 6 faces selected, then now I'm ready to assign the voltage. So now what I do is I right click and I go to assign excitation, and this time I'm going to choose voltage, and I'm just going to leave the default settings of 0. So this is a representation of a point charge that's sitting in free space. One caveat is if you start evaluating fields that get close to the boundary, we ultimately have a truncated boundary. So what you start to see is the effects of a forced 0 voltage in areas that won't really comply with the laws that we describe. So all the work that we're going to be doing is going to be taking place far away from that boundary, and sometimes that can be very important as we're trying to validate some of these things. So I'll try to make that clear as we continue on through the session. So our physical problem is actually set up. We could run this if we wanted to. We have to set up a couple of other objects, and I'll explain them as we go. So first, I want to hide this sphere. I'm still in face mode, so I can either right-click in the dead space and choose selection mode of objects, or I also could have hit the letter O. So I don't need this this bounding region right now, so I'm just going to hide it from view. With it selected, I can just hit the X. That's not delete. It says hide selected objects in the active view. If I want to get it back up, I can bring everything back up like that. I can select again, and I can only hide this object. I can turn the other objects off. So you have lots of options to be able to do that. So with that hidden now, I'm going to zoom in, and what I'd like to do is set up the sphere that we want to use in Gauss's law, which is the integration sphere. In other words, the charge is going to be where you see it. We're going to encapsulate this charge in another just imaginary sphere, and that's what we're going to be applying the closed integration over. So I'm going to set this up as with something we call a non-model object. So we do the exact same operation. I'm going to make this 5 millimeters. So let's go back to draw sphere. You should be able to choose the center here. You'll see it highlight, and I can draw this out. And just like last time, I can either use the measured data on the side and wait till I get to 5 millimeters. It looks like maybe that's it. Yeah, it looks like that's actually it. So I'm at 5 millimeters. You can also come in and choose this and adjust it accordingly. But we're already at 5 millimeters, so that's good. I'm going to make this transparent. So by selecting that outer sphere, I can expand out my properties window here, and you'll see I can make it, I can choose whatever color I want. I'll choose a different color. I think in my notes from the last session, I used an orange dash line to represent the imaginary sphere that we're going to integrate over. So let's go ahead and make it orange, and I'll make it transparent so we can always see the charged object that's in there. So let me highlight that object again. I talked about a non-model object, and what that means is that it means the physics model. So this sphere is not going to be part of the physics model. It is part of the geometry model, but this toggle means let's not consider it as something that we're going to apply a charge to or a boundary. So let's just make it non-model by toggling this off. And by doing that, it ends up in a different category, which means it doesn't matter if it has a material or not. It's really not relevant. It's just an object that we need to refer to. So with that done, I'd like to make 2 more objects that are going to help us control and refine the accuracy of the solution. These are going to be boxes. So let's start by I want to put a box around each of these spheres. We'll put one around the charge sphere, so that should be sphere 1. So if I just go to this command up here that says draw a box, I'm going to put a box around this sphere. So let's make it, I'll just draw it out. However, it doesn't matter because I'm going to adjust these dimensions in a second. If the sphere of the charge was 0.5 millimeters, let's make this 1 millimeter so that it completely encloses it. So I'll say position will be negative 0.5, comma, negative 0.5, comma, negative 0.5, and then the size will be 1 in all directions. And I'm going to make it so that if I select the object, I can just make it transparent, and I'll make this blue. Just a different color. Okay, so I've got that. By the way, this should also be a non-model object. So we're not using this for the physics. We're using this just for the geometry to be able to put some operations on it. So I'm going to turn model off, and you'll see it should move up to the non-model category. We'll do this one more time just to refresh myself. This larger sphere 1, this one, sphere 2, looks like we made it 5 millimeters. So let's make this box of 10 millimeters on a side. So if I create a box, I'll just drop it anywhere, and then let's go ahead and adjust this box too, and I'll make it negative 5, comma, negative 5, comma, negative 5 in the position. And if we make it 10 in all directions, then it should be, if I did this right, it should be completely enclosing the sphere. And we'll just leave this as a separate color. So that's what we're looking for. And again, this is also a non-model object, so let's make sure that we choose the box 2, and then we'll turn model off. So if you've made it this far, you should be able to verify that you've got the same objects in the non-model category. You've got the same objects in the vacuum category. These excitations are existing. We've set them up. You've got a charge on the small sphere. You've got a voltage on the large box. I had it hidden in my view. Remember, you can always turn it on just by hitting the green check mark. So, and then the other thing is that we have a setup that we actually, I may not have gone over the setup from a previous evaluation, but if I hadn't done that, I'll go ahead and delete this so I can show you how I set that up. I'm going to say add solution setup, and the default value here is a number of passes and percentage error. We're going to change the 1 to 0.1 for now, and we'll see if we like the results. Then maybe we'll leave the settings. These are things that we can change to improve the accuracy of the simulation, but we can't run a solution without having the solution set up. So let's just go with this for now. And the other thing that I would like to do is change the mesh, initial mesh settings. So our initial mesh settings, they default to these values. I want to change auto to classic, toggle off, apply curvilinear. I want to toggle on dynamic resolution, and then I want to slide this bar up to fine. And we'll see if that's too fine of a solution, because we pay the price in the simulation time, and we won't know until we try it. But I want to get some pretty accurate results, so I'm going with a fine solution in this case. The last things I need to do to improve the accuracy, we can come back and we might change these values depending on how long this takes. But I'm going to choose the box. I'm going to choose the inner box, actually. Let me zoom in, and I'll choose this box 1. I'm going to right-click on that box and choose to assign mesh operations. And I'm going to choose inside the selection, and it's going to be length-based. And instead of 0.2, we'll go with 0.1. And instead of, let's see, I'll do a similar mesh operation on the larger box. I'll right-click that one, and I'll say assign mesh operation, inside selection, length-based, and instead of 2 millimeters, we'll go with 1 millimeter. And let's see if this gives us a valid solution. That should be everything that we need. I'm going to go to simulation. I'm going to validate, and that looks good. What I'm going to do now is I'm not really sure if these settings are going to be an overkill that makes us wait a long time for a result. So I'm going to pause while I hit the simulation button. I recommend you do the same. If you're patient and you have time and it's going on for a few minutes, then you could just let it run, check the status bar, and I should be coming back very shortly to comment on what happened with my simulation. So let me just hit the Analyze All button, and I'll leave you with that. You should see a very similar activity going on. The progress bar is going to start cycling through a little bit. You should see some notes that pop up in the window here. It should give you some status if things have completed, and the same thing on the right-hand side. And you'll see it's going to go into this adaptive. It'll talk about passes in a little bit once it makes it past this stage. So let's see how this goes, and maybe we'll come back and make some changes. Now, if you look at the timestamps down here, you can see that simulation with the settings that I gave it actually ran pretty quickly. So just a couple minutes, and it looks like we have a result. I'm going to go right to the field calculator. And what I want to do is apply the operations on the sphere that is basically, let me just hide these. If I select, I can hold Control H to hide as well. I don't need these objects in my view is what I'm trying to show. So the only really thing that was involved in the calculation was the boundary of the outside and this charged sphere. So what this is the imaginary sphere that I want to integrate over. So if I can apply the calculation E dot dA over the entire sphere and the integral of E dot dA, then I should determine what the charge was inside. So let's just run that real quick without going into too many details of how to use the field calculator. I'll make sure that we leave a reference to a document that I guess spends a little bit more time walking through those steps and documenting that process. So all I did was right-click Field Overlays, and now I have Fields Calculator. So let's just go through and build up the stack here to get that result. So the first thing I want to do is pull up in the input field, I want quantity of E field. Okay, so now it shows up in my stack like that. And now I want to put the input geometry to the surface that I'm integrating over. So that's the sphere that we're looking at. So if I go to Geometry next, and I choose Surface, and I believe it's should be Sphere 2, if I'm not mistaken. And I will OK that. And then now what I want to do is run the normal calculation. So underneath the vector column, I go down to normal. And watch what happens to the two entities in the stack when I hit normal. It builds up this function, and it's telling me that it's a scalar value, and it's going to do the dot product of the E field to the surface normal of that sphere. So it's a lot of math that takes place just with one simple command line. Now with that, I'm actually going to perform the integration. So I'll go to the integrate sign. Okay, and now it changes it again. It's letting me know that it's still a scalar value, and now integrate is a new function that's going to be applied basically to the stack. So now what I can do is go to the output, and I can say evaluate, and it's going to take a little bit of time to pull the information from the fields, and we'll talk about that when we're done. And we get a value now. And now in order to validate Gauss's law, I know that the last thing that I need to do is multiply this by epsilon naught to pull out the charge. So let me go ahead and do that. I'll go ahead and put a constant, and I'll choose epsilon naught, and I'm going to multiply these two together, and the number that I get is should be identical to the value that I assigned the charge on that sphere. And you'll notice with some rounding here, if I was to round off to 4 or 5 significant digits here, then that value would actually be 1.0, or 1. So in this case, I can see that the result that I got from integrating over that sphere turns out to be the same result, the same input that we gave that charged sphere. So we get a value, we put a value of 1, and we just verified that by applying the integral to that enclosing sphere, we got the same result. So that's exactly what we were hoping to do. And this might be redundant, but just a clarification, the reason that we multiplied that final result by epsilon naught is because what we built up in the stack was ultimately the integration of the E field with the surface, with the dot product of the surface area around the entire sphere 2. And that doesn't give us the charge enclosed. It gives us the charge enclosed divided by epsilon naught. So by bringing that epsilon naught over to this side, we're only left with Q enclosed, which, as you saw, we got the value of 1. So here's the reference where I got this information from, and you can certainly find this in other text as well.